Section 3.10 is about local linear approximations. And these words, local linear approximation, are just a fancy way of saying tangent line. Okay, so we'll discuss that more as we work through our example. We've got a two-part question. Part A, we're asked to find the local linear approximation, which means tangent line, to f of x equals the square root of x at this particular point. X naught is equal to 25. And I've just put over here that we could phrase that a different way. We could say find the linearization. Okay, so finding the local linear approximation, we can condense that into one word, the linearization of a function. So let me just draw a picture and then we'll talk about this vocabulary. Okay. I know that the square root function looks something like this. Now it just exists in quadrant 1, so I just graphed quadrant 1. Okay. And at the point where x is 25, we've got this lovely point here, 25, comma 5. Okay. Now I know how to calculate the tangent line at that point, and we will be calculating it in a moment. Let me just draw in the picture. We've been saying all semester the tangent line is the line that best approximates a function at and near the point of tangency. And so you can see that the line is actually very close to the curve as long as we stay fairly close to that point of tangency. If you use a graphing calculator or a graphing program with zooming technology, if you zoom in on the graph of a curve that's differentiable enough, it starts to look like a line. It starts to look like that tangent line. That's because the line is really, really close to the curve. It's doing a good job of approximating what the curve is doing because they have the same behavior just at that particular point. Okay, so we call the tangent line the local linear approximation. It's linear, it's a line. It's an approximation. We can use the line to approximate the curve, which is what we're going to be doing in part B. Basically, values on a line are easy to calculate. Values on a curve are sometimes more difficult to calculate. So if we know that the line is close to the curve, then we can say, let's just find the value on the line. That's going to be a lot easier, and it's going to be close. Okay. But we have to qualify. It's the local linear approximation because the tangent line only does a good job of approximating the function at and near the point of tangency. If I go too far to the left, the line still exists, the function ceases to exist at all. And if I go too far to the right, this line is going to end up being really high up above the graph of the square root function because the line doesn't change how steep it is, but the square root function gets less steep the further we move to the right. So it's the local linear approximation. It does a good job of approximating the function at and near the point of tangency. But if we go too far away, it ceases to do a good job. Okay, so that explains why we call it the local linear approximation. We also call it the linearization to emphasize that when we're going to use the line to approximate the function value, it's almost like we morph the curve into a line. We turn it into a line. We don't really turn it into a line. We say it's close to this line, but we switch to working with the line. So linearization just sort of emphasizes the active part of that process. We are making a change from working with the curve to working with the line that approximates it. We're going from here to the blue line here, and then we'll use that to approximate function values. Okay, so let's see if we can't do this problem. So if we're finding the local linear approximation, we're finding the tangent line. I know we need two things. We need a point and we need the slope. Now for the point, we were given the x value, that's 25. The y value I've actually already calculated, but we get the y value by simply plugging into the function. And of course, the square root of 25 is 5. Okay, finding the slope, that's going to be a two-step process. We need to find a formula for the derivative function, and once we have that, we can plug in 25 to get the numeric value of the slope of this particular line. So, f prime of x, we're taking the derivative of x to the 1/2. That's 1/2 x to the negative 1/2. And since we're going to be plugging in a number, I'm going to rewrite that negative 1/2 power as just the square root of x in the denominator. And then I can say f prime of 25 is 1 over 2 root 25. That's 1 over 2 times 5, so that's 1/10. So the slope of this line is 1/10. All right, excellent. So then I can put the pieces together. Let's see. Always need space. Okay, I'm just going to make a note. The point here was, well, actually, I've got the point drawn there, so I'm not going to forget it. Okay, so rise equals slope times run. The rise is just y minus 5. Remember, we're calculating the rise using this point and essentially an arbitrary point xy somewhere on the line. And we're saying if we use that point to calculate the rise and the run and it goes with the right slope, it's got to be a point on the line. So y minus 5 equals the slope of 1/10 times the run would be x minus 25. Okay. And I'm going to just take this one step further. I'm going to solve it for y, so I'm going to add that 5 over. And then I'm going to give this a name. Okay. Because for this function, I could have written y equals the square root of x. But if I call it f of x, I know that that's talking about the y value on the curve. If I just call things y, I've got two different functions here. I've got the linear function and I've got the square root function. If I just call them y, it becomes a little bit unclear at times which y am I talking about, the y value on the curve or the y value on the line. So I'm going to just give this a name. I'm going to call it L of x. L because it's a line. So L of x is 1/10 x minus 25 plus 5. That's the function whose output is the y value on the line. So just like f of x is a fancy name for the y value on the curve, L of x is a fancy name for the y value on the line. Okay, excellent. So that's part A. We have found our local linear approximation. Okay, now part B, we want to use our answer to estimate the square root of 24.9. So here's what's going on. Now I'm going to purposely draw this completely not to scale, because if I draw things in this region where the line and the curve are close, it's going to be hard for you to see what's going on. So I'm going to put 24.9 over here. Obviously that is not to scale, but if you did look at the rest of this, you could imagine if we zoomed in on this enough, it could make that distance, that gap between the curve and the line, big enough to really see a little bit better. Okay. So what's happening is the square root of 24.9, that's the y value on the curve at that particular point. We're going to say, oh, that's close to the point on the line. Okay. So here, this point would have the same x value, but the y value would be L of 24.9. We're going to calculate that because we're saying they're close. So I can say this y value is close to that y value. Okay. So essentially we're saying root 24.9, that's equal to f of 24.9. That's the y value on the curve that I get when I plug in this x value. We're saying, hey, but that's close to L of 24.9. that's close to the y value on the line. And unlike f of 24.9, which I would probably want to use a calculator, even though that would just give me a decimal approximation, it would be a pretty accurate one. Okay, this I can calculate by hand. Okay, because this would just be 1/10 of 24.9 minus 25 plus 5. So let's see, that's going to be 1/10 of negative 0.1 plus 5. Now, it's a little bit odd to have fractions and decimals, so I'm just going to rewrite that 1/10 as a decimal. That's 0.1 times negative 0.1 plus 5. That's negative 0.01 plus 5. That's 4.98. Okay. Now, I knew that the square root of 24.9 should be a little bit smaller than 5, because this is a little bit smaller than 25, whose square root was 5. But using the tangent line, or the local linear approximation, helps me to get a slightly more accurate approximation than just it's a little smaller than 5.